today we are honored to have Professor Takeo Igarashi to give us a talk. Yeah, Professor Takeo is well-known computer graphics and CI expert. Uh, Today he will give us a talk entitled "Human in the Loop: Computational Design." So we also invite Professor Ligang Liu from University of Science and Technology of China and Professor Peng Song from Singapore University of Technology and Design to participate in our panel discussion. So for our audience, please leave your question in YouTube chat window or the other live stream platform. So our speaker and the panelists will answer your questions during the panel discussion. Okay, now let's move to the talk.
Okay, yeah, so let me start. So thank you first as organizers of this seminar. I appreciate this opportunity. So yeah, I'm working on somewhere between human-computer
Today
interaction
we are
and
honored to have.
graphics. And today I will more focus on graphics side of our group's activity. So title is Human in the Loop Computational Design. So before diving into this talk, let me briefly introduce my previous work to introduce my background. So yeah, as I said, I have been working on both user interface and then computer graphics. On the interaction side, we are trying to develop new way of interaction with computers. And I think this is a good example. So this project is yeah, a little bit old, but the idea is 3D modeling interface has so many buttons and menus. But here we try to minimize the number of buttons and menus, and everything is based on prediction or suggestion based. So suppose you have three lines in the scene, and if you highlight element, then system suggests possible operation related to the highlighted one, like triangle, box, or drawing surface. Or you can highlight three, then with these three things, the system predicts this drawing box. And if you highlight this box, system suggests drawing plane. And if you, for example, if you have this triangle and highlight it, then system suggests to make a triangle. And if you highlight these three, then system predicts extrusion. So this way, so you can just repeat highlight and selection, highlight selection, and then there's no need to search for buttons and menus. So that's the idea. So another, this is my PhD project already 20 years ago. But so you may already know this, but this is a sketch-based interface. So user draw something, and then you can get reasonable 3D shapes just by sketching and repeating. One thing I want to emphasize here is that application of this in mind was communication. Suppose this is say this is a stomach, right? And then doctor can say this is a three-dimensional shape of your stomach, and you have a serious problem here. And then let's remove this way. Oh, sorry, I will say this way and so on. So this kind of interaction and communication was the original motivation behind the system. Okay, so that's the background. And yeah, so let me dive into the topic of this today. So computational design is a process of asking computers to work on the design, right? So user first gives requirements or specification to the system, and then system generates some artifact. The result can be image, result can be 3D shape, or results can be physical object. And then system runs something like optimization or simulation, or more recently, machine learning approaches. So this is a kind of typical workflow in computational design systems or computation design processes. So let me look at this process more closely. So typical approach is the system takes requirements and then run computation and the artifact. And there was no user here usually. But in our project, we try to, look into possibilities, what we can do better by putting human in this computation process. So that's the idea. So not only putting requirement at the beginning, we want to do human to interact with the system during the computation process. So that's a basic idea. And yeah, there are a couple of benefits here. So first, it supports creative exploration, right? So, design and fabrication is exploration process. User cannot know the result, ideal design at the beginning. So user have to see the result and understand constraints and then revise the idea and then see feedback. So this kind of iterative process is critical for design activities. And we can also exploit human perception in the computation, right? So your computers cannot see the world as we see. So, and it's important to human in the loop to exploit human perception, such like aesthetics and so on, and also personal preferences. So that's kind of thing. And finally, so by using human in the loop, we can also use the physical capability of people. So that's the kind of benefits in having human in the loop. So so today I will talk about 3 topics. One is computational design, human in the loop computational design with physical simulation, and then also human in the loop computation design crowdsourcing, and also talk a little bit about with smart devices. Okay, the first one, physical simulation. So the human in the loop computational design with physical simulation. So the idea is like this. So standard computational design system or CAD system is usually, how to say, like line drawing. So there's no physical world awareness. Like system in the typical 3D modeling process, system doesn't understand real world constraints like collisions, frictions, gravity, material property, and so on. So in this, these constraints must be taken care of by experts in their head. However, if we have a physical simulation inside a modeling system, then system can support user to design artifact satisfying physical constraints. So that's the idea. So so the first project we looked into this in direction was a stuffed animal design system. So Teddy was very good for 3D modeling, but it doesn't understand physical constraint. But here, the system take care of the physical constraint. So let's see. So the interface is very similar to Teddy. So user draw something, and then system will generate 3D shape and present it to the user. The interesting point here is that system also shows a 2D cross pattern for creating this stuffed animal. So system runs physical simulation to predict the result of fabrication on the left-hand side. In order to get a stuffed animal, you have to design 2D texture garment pattern, cross pattern. But it's not easy for novices. But with this kind of simulation, even novice users can design reasonable 3D shape with appropriate 2D cross pattern. So by repeating this kind of operation, user eventually can generate some reasonable 3D shape just by drawing operations. And then user physically cut and stitch cross pattern together, you will get a physical artifact. And you can also make a big balloon by using the same pattern. And we ran a user study with kids, and they successfully designed their own original one-of-a-kind stuffed animal, and then they fabricated them with the help of parents and so on. So that's the idea. Okay, and then, so this one is metaphone design system. So this is a kind of strange topic, but suppose you want to design a special metaphone, and I hope you understand it's not easy. So it should look like good. It looks reasonable, but also it have to produce appropriate sound, right? But it's very difficult for a human to predict what kind of sound they produce from its shape. But computer can simulate and predict. So by combining two-dimensional geometry editing with sound simulation, then it's very helpful for designing your own new metaphone design. So that's the idea.
It's also updated with overlaid via. In this example,
yeah, I hope you hear the sound. And so you have a cross two-dimensional pattern on the left, and user edit the cross two-dimensional pattern. And on the right-hand side, you see a physical vibration analysis result. You can see in this area vibrates a lot, and then this one is fixed. And also you hear the sound is a prediction of the sound it may produce when hit by a bar.
the tone of a metal phone is calculated via eigenvalue analysis. As the user edits the metal phone's shape in the left window, the system immediately computes its eigenmode showing the right window, which tells how the metal phone oscillates in 3D space. Its tone is also updated with oral feedback using beep sounds and visual feedback in the status bar. Because the change of tone caused by the shape edit is very difficult to predict, we believe designing a metal phone with a desired shape and tone will be possible only with a responsive FEM.
So
Some
that's
pieces
the
by an
idea,
artist.
and then here's the result. And
And
we
its
also,
actual creation.
yeah, physically created.
This shows that our analysis successfully simulates the real world.
Yeah, so I think it's kind of difficult to do this without real-time feedback from the system. And we also apply the very same idea to a garment design. So user edits the two-dimensional garment pattern on the left, and then system continuously runs garment draping simulation on the right. So the user can edit two-dimensional pattern appropriately by directly observing 3D results. So that's the idea. So yeah, again, the idea is the same. On the left, you have a two-dimensional design. So user edit it as a 2D drawing editor. But on the right-hand side, you continuously see the simulation result. So user can directly observe wrinkles and stretching, and then you can directly edit on the left-hand side. I hope you understand that this is very tedious in traditional workflow because users have to physically cut garment across and then put in a mannequin and then look at result and then go back to the 2D cross pattern and go back and forth. But here, everything is directly connected and you can edit the 2D pattern so that the 3D draping result looks good. For example, if you see wrinkle here, then you can cut out the cross pattern and then you can fix the problem there. So that's the idea. And this kind of system is very useful for 3D strange 3D body shape like this kind of monster. So we don't have any idea how to design a garment here, but you can directly observe the 3D result while designing the 2D garment pattern. So again, if you have a problem here, then you can cut out and then you can fix. Yeah. And we actually fabricated the character and the garment, and of course it's not exact match, but I think it is producing reasonable shape. And we also tested this technique with real human body like this way. So yeah, it's fun to put real clothing on a real human like this way. Okay. So the last one, or not the last, but this one is paper airplane, paper glider design. So suppose you want to design an original custom shaped paper glider. However, it's very difficult to make it really fly, right? So very detailed design variations make it fly or not, and it's very difficult for the user to design original glider design. However, if computers help, then it's possible to design really flyable gliders. So that's the idea. So video start with failure case, I think. Yeah, so this looks good, but arbitrary design doesn't fly. However, if this is a design result using our system, So it looks like some particular character, and then it really flies. So that's the idea. And then, so this is a user interface of the system. It's very similar to the garment design one. So user just freely edit and design a glider shape, and the system continuously runs flight simulation below. So this is a side view. So the glider ideally flies all the starting point through all the way through, but sometimes it goes up and down or just drop. So the goal is to make it fly from left to right long way. So user can continuously observe the flight trajectory, and then user edits the 3D shape of the glider. So the problem is that in some cases, it's very difficult to make this really flies by manual adjustment. So the system has a magic button here. Can you read this? It says make it fly. So when the user press this button, system runs optimization so that the glider actually flies best. So yeah, be careful. So if when the user press this button, system automatically adjusts the glider shape. So please watch it. So user press it, and then system make adjustment here, and then it flies better. An interesting thing here is that this can be cooperative. So user manually edits the front wing, and the system automatically edits the rear wing. So this is a kind of collaboration between a user and computer. So user edits the front wing, and the system adjusts the rear wing. So in this way, a user can explore the design space with the help from a computer. And after finishing the design, we can just send the data to the fabrication device, laser cutter in this case, and then assemble together. And then it will fly. Yeah. Okay, so that's the idea. And so technically, interesting aspect with this project is that we took data-driven approach. So typical approach to run this kind of simulation is a more accurate fluid dynamic simulation, but it's too slow for this kind of interactive design. So here we take a data-driven approach to manually fabricated many gliders, and actually slow them and then measure the flight trajectory, and we analyze, and then we use this kind of many measure data to predict the trajectory of the current design in this system. So that's a novelty in this project. This is our latest result in fabrication project. So this is an interactive design and fabrication of wood joints. So this image basically explains everything. So the goal is to design custom design joint like this one using a milling machine. And user interactively edits the joints, and then system predicts feedback, and then user eventually get into a desired design. So let me show you a video. So let me skip first part. Where's the best place? Oh, no, sorry. Yeah, so this is a user interface. So it's basically a very simple voxel design system. So user opens the joint, and then push and pull the voxels, and then system continuously provides feedback when there's a problem with the current design. So after having a design, so we send it to the milling machine like this way, and then you can get many various kinds of fabricated results. So like this one. So this is great because we can create furnitures and so on without any nails or metal joint things and so on. So these are the kind of constraints we provide feedback, like connectivity constraint, bridging constraint, and milling direction, and so on. And slidability, the joints should only slide in one direction, so on. And yeah, durability or contact area and so on. And I think the most important feature of this paper is the fabrication constraint. We not only consider the physical property of the final product, we also consider the fabrication process. In this case, we use 3D 3-axis milling machine. So we put constrain the design space to be fabricatable with this particular hardware device. That's the thing. Okay, so that's a physical simulation part. So computation design of physical object with physical simulation. So that's the first part of this talk. So let me move on to the second part is crowdsourcing. With how to say, with Amazon Mechanical Turk kind of thing, crowdsourcing gets popular. And we are seeking possibility of bringing crowd into the human in the loop computation design process. So yeah, human in the loop computation design with crowds. So yeah, basic idea is simple. We have a computer and then system computes a final product. But during the way, we take input from human crowd workers to do something not possible with computers alone. So that's a basic idea. And we worked on a couple of projects based on this idea. An important thing with this setup is that crowd can only do very, very simple tasks. So each crowd worker can only do very simple thing, but we can aggregate it. Then we can do something more than simple things. So that's the idea. And then, yeah, this is this is a collaborative 3D modeling by the crowd. And I would say this is not too successful research project, but nonetheless, I think it was very interesting. So I want to share our experience with you. So yeah, the problem is 3D modeling is still difficult. So many buttons, so many birds, so many things to learn. So the motivation here is what about we divide the complicated 3D modeling process into small tasks and then ask them to each of them do very, very simple tasks and then aggregate. Then it might be possible to do 3D modeling without intensive training or intensive learning. So that's motivation behind the project. And yeah, specific contributions, novelty here is a task design and workflow design. So let me go into details. So this is a task design part. So this is a crowd worker's task. It's simple single view 2D drawing editor. So 3D modeling is very difficult, but 2D drawing should be easy. So that's the idea. So each crowd worker's task is to draw, one projection, axis aligned projection view of one view. So that's the idea. So this is a task of one crowd worker have to draw projects from this viewing direction. And then the task is to just draw approximate look of this object from this viewing angle. So it is very simple, just simple boxes and then reshape and moving, dragging around. So that's, we try to simplify the user task. So user do something like this to draw this chair. So just a 2D view of this complicated 3D model. And after users draw side view, front view, top view, and then system runs aggregation. Aggregation part. So this is a user drawn things. And then we cluster similar images, similar drawings, and then take the biggest cluster, basically, like a majority voting. And then we also aggregate and take average in essence. That's the idea. Pick the largest cluster and take average to get the very best from the users, multiple crowd workers. And the problem is that we run this, then result look like this, because user drawing is so poor and so divergent. So it's very difficult for computer to get real result from the user's first initial input. right? So this is the result, but so many parts are missing. So that was a challenge. So we put additional workflow step. So sketch workers generate many sketches, and then we recruit other set of cloud workers to review it, and then get best result, and then show it to the next round of cloud workers, and then get better. So this is kind of iterative refinement process. With this step, we finally successfully generate 3D shape. This is the first result, first iteration, and this is second iteration, and then again, expert reviewers select the best ones, and then third cloud worker set worked on the next stage. So that's the idea. And we successfully generated these 3D models purely by aggregating 2D drawings from cloud workers. However, the problem is that it turned out to be not too cheap. It's actually expensive. So that's a limitation of this project. So yeah, so this is a comparison. So this is a result by cloud workers, and this is a result by expert users. And unfortunately, quality was higher with expert, and cost was actually cheaper with expert. However, still we do have some merits here. So the problem with expert is that we have to identify or recruit specific expert human, and it's not easy, right? You have to put a call and then email communication to negotiate prices and explain specifications. It takes time to start and have them work it. However, cloud workers' benefit is that people are everywhere. We can do anybody who has extra 10 minutes or 5 minutes of spare time. So turnaround time is much shorter here. And also, so labor means labor from end user, like customer's point of view. So if we use our workflow, user only needs a photograph and then just few clicks to everything is taken care of by the system. But if you need to recruit expert by yourself, you have to communicate with potential candidates, negotiate, explain tasks. It takes, it's tedious. So yeah, this money justifies this quick turnaround and also minimize human labor from customer's point of view. Okay, so that was our 3D modeling. And next one is crowdsourcing of Photoshop image editing, the idea. So the problem is here. So parameter tweaking is a target task here. So a typical example is Photoshop image enhancement. You have many parameters like brightness control, so white balance, and so you have many sliders, and you have to manually edit it, which is very difficult. Also, parameter control appears everywhere. Another example is computer graphics material design. So you have many material properties like BRDF parameters and so on. So this kind of parameter tweaking is very tedious for users, and it's very hard for novices, and it's also still tedious for expert users because manual search is very high dimensional, and it's very hard to navigate in high dimensional space because you have to make a mental model of the high dimensional space. So that's a target task. And our idea is to divide this complicated parameter tuning task into crowd working tasks, so crowdsourcing. And again, the idea is to decompose complicated tasks into a set of small, simple tasks. And then here's our contributions here. One is microtask design, and another is algorithm framework to do this. And microtask design. So typical approach in crowdsourcing for design task is pairwise comparison. So this is very popular de facto standard approach. So as system shows 2 results or maybe 3 multiple results, and then the user chooses the best one by clicking. So this is very simple and very popular approach for crowdsourcing. However, problem here is that information you get from this very simple binary input is very limited. So our idea here, our proposal is to use slider. to get more continuous rich information from a crowd worker. So user is presented with an image with slider, and the user manipulates the slider and then see variations of the image. And then user just selects the best one within the given range and then return it to the system. So in this way, the system can provide much richer information, which result in a faster convergence of the results. So that's the idea. And we also use a Bayesian optimization technique for this crowdsourcing aggregation. So Bayesian optimization is a machine learning technique to find optimum with minimum number of queries. So the system chooses most informative query and then iteratively update the estimate. So this can be seen as an active learning kind of approach. So yeah, so this is a brief overview of Bayesian optimization. And if you only have only sample, only single one, so suppose you have a parameter space on the horizontal axis, and then cost function, value function to the vertical axis. And then suppose you have a ground truth is this a dotted line. But if you have only single observation, system projection is very flat. Then system decides, let's ask question here, and then the system the user answer question here, then system updates the prediction. And then system, then let's ask the question here, and ask question, they get the user result, and this is updated estimation. So in this way, the system sends query to the user, and the user returns the answer, and the system updates the prediction and the estimate. And then iteratively, system finds the best solution. So that's the idea. So we evaluated this among single slider manipulation, so our proposed method, and also pairwise comparison, and also four-way comparison. So these two as a baseline approach. And the result was very good. So this is average. So horizontal axis is iteration, and vertical axis is error to the ground truth result. And as our method, much faster convergence, and then also much better convergence at the very end. So yeah, so that's the idea. So we tested with this Photoshop image editing and also material design. So user only gives a query like, please give parameters for gold teapot material. And then crowd worker work together to get set of BRDF parameters for gold materials. Okay, so that was sequential line search paper. Okay, let me move on to the next topic. This is, this was most recent result. So this is a human in the loop differential subspace search in high dimensional latent space. So the idea is very similar to the previous one. So user repeatedly, iteratively provides slider control to the system, and the system searches for the parameter space. But here, the target problem is neural image synthesis, like a GAN, generative adversarial neural network. The problem here is that this is a very, very high dimensional parameter space. Previous one, this sequential line search one. Let me go back. So previous one was a Photoshop parameter space. So the dimension not so high. So latent parameter space dimension was like 3, 5, 7, something like that. However, this kind of latent space dimension is very large, like 512 by 512 or something like that. So it's so high. And it's known that Bayesian optimization doesn't work for very high dimensional. So that's a problem. And in this project, we take an approach of differential subspace search, which means we analyze the structure of the neural network synthesis model and then leverage that information for identifying the best question to ask to the user. I hope you get the idea, but let me first show you a video. So we apply the idea to a couple of example tasks. So one example is synthesis of MNIST images. So suppose user's task is to find the latent vector that produce this target image. And this is a user interface. So user searches, one-dimensional subspace and then set return next, and then return set press next. So I hope you get the idea. So user repeats one-dimensional subspace search, and then you eventually get the result. So another example is ShapeNet image. So 3D modeling, generative modeling of 3D shape. Again, this is a very high dimensional parameter space, but the user only work on a single one-dimensional subspace search, repeats it, and then you will get the target. That's it. So yeah, each iteration is very simple one-dimensional search, but you repeat many times, and then this one-dimensional spans in many different directions in the high-dimensional space, and then you eventually find a reasonable result by after a couple of iterations. And this technique can also be
For a sound
usable
generative
for
model.
sound generation. So I think sound is a very good example of this one, because if it's a 2D image or 3D image, you can actually directly specify the constraints or preferences. But sound, it's very difficult to explain. If you want to have a dog barking or glass shattering, it's very difficult to explain what kind of sound you want to the system. But with this kind of search, user only needs to answer questions one by one. This is better, this is better, this is better. And you will eventually get the best latent vector. So that's the overview. And let me go a little bit more into details. So user interface I just explained. So this is the basic idea. So you have a neural network that takes a latent variable, and the network generates a created data. And then human perception user watches it and then judges whether it's good or not. And we formulate it as with this kind of equal formula. So G is a latent vector, F is a result of neural network, and G is a human perception. And we want to find the maximum of human evaluation result. So that's the idea. However, this is black box from computer's point of view, but this is no model for the computer. So we analyze this part. So again, so this is optimization problem. We want to solve a combination of network and human perception. And then we try to solve this with a typical gradient descent method. So zk1 equals zk plus delta, and delta is alpha by gradient. This is a gradient. And then we took this gradient part to look into more closely. Then we can decompose this gradient into human neural network gradient part and human perception gradient part. And of course, human perception gradient parts, you cannot know anything. System don't know anything about it. However, this neural network gradient part, we can analyze it. And then we run singular value decomposition to this neural network gradient, and then pick the most dominant directions. So this is the most important part. So pick dominant direction. So this is a high dimensional space. User can go many ways, but only particular direction you can see huge change in the final result. In some directions, if you even move, you don't see any change. So the basic most important point here is that pick dominant ones, the biggest eigen singular value directions, and then only present it to the user. So in this way, in the end, you will get this kind of formulation for the gradient. delta part. So system computes this gradient directions, and then it essentially maps the problem to a low-dimensional subspace. And W is actually the value provided by the user. So user provides W, which means perception part of the system, and the system computes the system part here. And this is a much reduced subspace. So that's the idea. And here's the illustration of the subspace. The first one is the biggest singular value. So direction subspace where the biggest change in the final result. So as you see from the starting from the center, slight change in the parameter result in a huge change in the final result. However, if you look at the last one, I think 256 small singular value area, as you see, even if the user changes the parameter, the result doesn't change a lot. So as you see here, it's much more effective to show this variation to the user than showing this variation to the user. So that's the idea. And here is an experimental result. So this score gets much better using our technique. And unfortunately, in the random subspace or Bayesian optimization doesn't work well for this kind of high dimension. So that's the result. Okay, so the next one is we present this at SIGGRAPH Asia 2017. So how to say, this project is slightly different from previous one because it's not cloud, but as a technology we use is similar. So I want to introduce this paper here. So this is a very different topic again. So this is fully perceptual based 3D spatial sound individualization with an adaptive variation autoencoder. So the target task is 3D spatial sound, and then individualization. And then we use it by using a neural network, also machine learning approach. So that's the idea. So this is a background. So our target is 3D sound rendering. Spatializing sound at an arbitrary position using stereo headphone. So I think this is a basic idea. So suppose you have a headphone and then try to represent sound coming from arbitrary direction, like from top, or from front, or from back. And people can distinguish sound from back and front by observing the sound modulation by a filter consisting of your physical ear and physical head structure. So 3D sound rendering achieved by a convolution of HRTF filter with switching to the direction. The problem is that this kind of filter is highly individual. Each person have a different filter, so it's very difficult to truly represent spatial audio for individual user because we don't know the individual user's HRTF filter parameters. So that's a problem. And traditional approach to this problem is that measurement. So you put a human subject, particular user in a specific room, and then produce sound from all directions, and then measure the response from the recording in your microphone in your ear. So that's very expensive and time consuming. So that's a problem we wanted to address. So we tried to address this problem by machine learning approach. So in pre-training, we take pre-recorded, pre-measured HRTF data set, and then we train a neural network such a way that it can separate individuality part and then general common part. And after the training, in the runtime, system produces some test sound, and user provides subjective perceptual feedback, and the system updates the parameter and provides feedback. So in a sense, so this calibration phase optimizes this weight by adjust the neural network parameters by using user feedback. So that's the idea. So this is a user's task. So you hear sound and then just answer which is better. So by repeating this process, a user get very, very nice spatial 3D audio result. So that's it. Okay, sorry, I'm running out of time, but so I first introduced computational design with physical simulation, and also human in the loop computation design with crowdsourcing, getting simple response from each individual user. And then finally, I will briefly talk about our projects in a smart device one. So yeah, human in the loop computation design with smart devices. So typical fabrication, digital fabrication is processed like this. So user do design on a computer and then send data to the fabrication device, and then you will get the result. However, this is very indirect, long way from user to the thing. If you see a problem in the thing, final result, you have to go back to the computer and edit it. So it's very tedious. So the idea behind direct fabrication is user direct to interact with a physical art result, so that you can put more rapid control, rapid iterative design exploration cycle in this fabrication. So this idea is not new. There's a couple very nice project results from other researchers, like a position correcting router, cutting device, or freehand digital sculpting a tool, by using user control and the system control work together. So these are the inspirations. And one project we worked on is a carpet drawing system. So let me explain. So the inspiration is here. As a childhood, you may have put drawing on a carpet. So we developed hardware systems to devices to carpet drawing. So one is raster graphics kind of thing. So we have this kind of roller, and then pins go up and down accordingly as you rotate, as you move on. So user just scrape the carpet surface with this device, and the system produces appropriate trace result in this way. So by repeating this process, the user has to go back and forth by himself, but everything is automatic, and you can get a very big picture like this one. And the second one is a vector graphics kind of thing. So the wheel is continuously rotating to raise the fur. But the problem is that you have to rotate this wheel in the specific orientation all the time, right? If you rotate the wheel in the wrong orientation, it never raises the fur. So that's a problem. So we put orientation sensor and actuator to keep the stabilize the orientation of the wheel. Right, so even if you are holding angle, pen body orientation changes, the pen tip wheel orientation is stabilized like this way. So if you use a finger, you cannot draw a trace if you move in the wrong orientation, wrong direction. But in this device, you can draw line in arbitrary orientation. So which is much better for drawing. So yeah, you can do something like this. And the final one is not very interactive, but if you have a ultrasound speaker array, you can remotely apply force to fur surface. So you can remotely activate and deactivate the fur surface. That's the thing. So yeah, just an overview. We also worked on architecture project. So as you see, this is a human being, and then we build this kind of big architecture scale structure with a device. And we designed and implemented physical hardware device to drop chopsticks from the box. And we also projector-based guidance system for guiding chopstick deposition. And then so the user just follows the instruction presented by projector image and then drop chopsticks accordingly. and then you will generate this kind of structure made by million chopsticks. That was a kind of fun architecture project. And we also experimented with a 3D architecture scale 3D doodler. I hope you know the 3D doodler. So user holds a pen and then draw physical line in the air by moving around. So we want to do the similar thing with architecture scale. And this is a video. So here is a device, and as you move, then structure hard pillar appears as you move the device. And then by using device, we fabricated this kind of architecture scale structure just by drawing a three-dimensional curve in 3D space. So yeah, I'm sorry, it's a talk. It's not so well organized, but that's it. So I implemented human in the loop computation design. So instead of just allow how the system do everything, user is in the loop to provide feedback. And we experimented with human in the loop computation design with physical simulation to give feedback about physical constraints, and with crowdsourcing to by decomposing tasks into small simple tasks. And also we experimented with couple of fabrication with smart devices, interactively interact with final artifact. So yeah, that's my talk. And finally, yeah, it's not so easy today because of this virus, COVID-19, but we are still hiring postdocs, interns, visitors, and hopefully, after this pandemic, I hope we get more visitors in your group. So yeah, if you are interested in, just send me an email and let's discuss details together. So yeah, that's it. Thank you.
Yeah, thanks for your wonderful talk. Yeah, so maybe we need to wait a few minutes to collect some questions from audience. But in the meantime, I think we can start to discuss some related topic from your talk. Let me, okay. Okay. So Peng, do you have any questions about the talk? Yeah.
Yeah, I have some questions. So thank you, Igarashi, for the nice talk. So my first question is that so in this human in the loop computational design, both humans and computers will be involved in the design process. So my question is, so what is there any criteria to distribute the work between the human and the computers? For example, what should be done by the humans and what should be done by computers?
So it's difficult to answer. In short, I think user should take a lead, right? User has a goal in mind. So the control should be given to the user. And then system should help take care of the low-level details. In other words, computer should do everything the computer can do. And then user should do something computer cannot do. So that's the idea. And then I think I already explained the talk. So user is very good at aesthetics evaluation or personal preferences. So these kind of things are very difficult for computers. And also in the final part of my talk, I discuss about human body. Human body is actually very capable. If you do the same thing with machine, you need a huge robot. However, if you can leverage human body, dexterity and power, you can do the rest by a small device. And the computers are very good at very detailed, precise control. So yeah, in the physical world, the user can do coarse, rough thing, big thing, and then computer can do the details. So yeah, so it should be complementary each other.
Yeah, that's true. Okay, and so concerning the last topic, computational design with smart devices. So now I understand that the human will use the body to control the devices. So what does the computer do in this topic?
So for example, in the what was that? Yeah, in this project, for example, the second part is the most good example. If you have a pen, and the user is just moving around. You want to draw a circle, draw a drawing, and then computer do its sensing and actuation. The system detects orientation of the pen, and then system adjusts orientation. And the similar thing for this previous work. So Alex system, user moves around the cutter roughly, and then system adjusts the very detailed location of the blade. Then you can get very detailed shape. Working system and human work together. The same thing here. User roughly move around the pen tip, and then computer decides the details.
Okay, yeah, that's correct. I have one more question. So from your talk, we know that it is a trend that we are going to apply this learning method to solve to help to solve computational design problem. So I'm wondering if you can share your insight about the trend of this human in the loop computational design. For example, what kind of emerging technology can be integrated for the design process?
Yeah, that's so you're saying, talking about recent machine learning techniques and this kind of process.
Yeah, that's one. But I'm wondering, is there any other emerging technology can help people to do this computational design?
Yeah, I think every emerging technology can have opportunity to do something new. As you see, these three things already motivated by recent emerging technology in these like 10 or 20 years, right? Physical real-time physical simulation was not possible like 30 years ago.
Yeah.
But recently, like 20 years ago, when we started this project, real-time physical simulation just get started, and in games. So we want to leverage it in our project. The same thing, crowdsourcing didn't exist before, and crowdsourcing was emerging new technology at that time with mechanical turk and so on. So we try to leverage it. And the same thing with smart devices. Small actuators, small sensors emerged. So yeah, I think this list goes on with new technologies appears like machine learning techniques or I don't know, something new. So yeah, that's what we do.
Okay. Actually, so okay, one more question. So concerning this computational design with physical simulation, actually, I also did some works in this area. I find that we not just use this physical simulation to help the computational design process. We find that sometimes when we do the computational design, especially for fabrication, we find that some existing simulation may not be sufficient. For example, when we do this rigid body simulation, we find that existing ones they usually have some very minor collision because sometimes they don't consider this collision as a hard constraint. Actually, they consider it as a soft constraint. But when we do the fabrication, actually we don't allow this. So so I just want to discuss with you that so is this computational design topic will also encourage some new problems or challenges for physically based simulation.
Yeah, so we didn't specifically worked on that project direction problem. But yeah, of course, physical simulation is never perfect. It's just abstraction and simplified problem. One interesting story I can share with you is this one is interesting with that topic. So here, again, sound simulation is not perfect. So if you design a shape with appropriate sound in simulator and they cut and then hit, it's slightly different. Then you have to, adjust it by, how to say, slightly removing the material from the physical metal plate. However, in that case, still simulation is helpful because it tells you which part you should reduce material. So this kind of, physical simulation is not accurate, but the result is also helpful for adjustment of the real world material. So yeah, you are right. So physical simulation is not right, and alignment of reality and physical simulation result is important thing to be aware of. Yes, you are right.
Okay. So I think I already asked lots of questions, so I just leave the floor to the audience or Lika.
Yeah. So I currently I didn't get too much input from the audience. Yeah. So Ligang?
Yes.
Yeah.
Okay, so let me ask some questions. Takeo, so next exploring talks, and I was enjoying the talk actually. So let me ask some minor questions in the Q&A session, and then we can discuss about some high-level topics afterwards. Okay, so the first one is I was quite inspired and interested in the work of crowdsourcing. So the idea of splitting the big task into some smaller ones and allow users to do something, and the machine or the algorithm can correct some rich information to help the user to design models. I, I I really like the idea. So, but some minor questions are raised. For example, how do you handle with the cases? For example, different users specify some constraints with conflicts. Uh, then, how the algorithm handles with these cases?
Yeah, so we didn't specifically try to address that kind of problem. In our system, it's basically just averaging or majority voting kind of logic we use. So yeah, that's the answer for now. However, I think there are many possible directions, such as subdivide crowd output into multiple clusters and then solve problems differently. So yeah, sorry, we didn't work on it, but yeah, I think that's important thing to talk about.
Yeah, so if you have lots of the collections, so maybe some conflict between the users in specification may not be a problem because they can be regarded as some noises or outliers, right?
Yeah.
But we have various types of users, and maybe this might be a serious problem. Yeah, when the crowding is become larger and larger.
Yeah, so
Okay,
there are a couple of work in artificial intelligence community did various algorithms for crowd input, and some of them discuss, selecting reliable crowds or unreliable crowd worker.
Okay.
So we can learn from them, I think.
Okay, yeah. So first, maybe you can clean the data for as some process procedure. Okay, something like that.
Yeah,
okay, I
there
see.
are a couple of sophisticated algorithms.
Yeah, I see. Yeah. Okay, so the second one is actually the idea is learn from user interactions. This is a very nice direction, I think. Yeah, because in the real world we have different kinds of human and human intentions. So how to learn the intention from the user interaction? So do you have some high level or some specific ideas about that?
How to learn user intention from
Intention, right. So for example, in the PS Photoshop parameter picking, some people like some style of lightning images, or some people maybe like some the other type of images. So this people has different intention or different styles. So this might be a high level learning some stuff. Yeah, maybe machine learning can do something, but I like to know what we will what do you think about this kind of issue?
Oh yeah, so I think that's I would say future work of our work. So
Okay.
we just focus on instance design, like instance of Photoshop result or instance of audio, but we didn't generalize it to a particular user's style or particular user's intention. A problem is that in order to distill particular user's preference, you need a lot of data from the particular user, and that can be a bottleneck, right? Typical machine learning starts with massive data from many people, and yeah, so that's a challenge, I think.
Okay, yeah. But this is a good direction, and as you say, this might be a very good direction in the future work. Yeah.
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 Yes.
Okay. I have also some ideas about that. So maybe we can discuss later. Okay. And
Yeah.
the work of differential subspace search is also very nice. And actually, as you mentioned in your talk, that the dimension of the latent space may be very high, and you reduce the dimension into some subspace, right? And then you
Yes.
allow the user to tweak some parameter uh, some numbers to get the results.
Yes.
But the task may be still very large.
Yes.
I mean, even you reduce the dimension, maybe the dimension may be still higher.
Yeah.
So you have to collect lots of user interactions, right?
Yes.
And in this way, maybe a very large neural network should be used, right? So can you talk about some details about that?
Yeah, so that's a kind of interesting research question. But interesting point with this research is that where was that? Yeah, this one, right? So yeah, it's I don't remember the exact number, but you can reach reasonable result with reasonable amount of iteration. So each one is very simple, like few seconds, and like 5 or 10 iterations, then you can get the result. So yeah, so experimental results suggest that you can get reasonable result with several iterations. Not bad.
Okay. So that's fine. So some small questions first. Okay, that's it. Maybe there's some questions from the audience.
Yeah, there's one question from the YouTube audience. Yeah, I think the question is more general. So he asks, is there any strategies to guide the new users to design ideal shapes as they want, typically in the industrial scenario? So some so people want to know whether you can using this kind of any kind of human in the loop approach to guide the user to design ideal shape. But I think he didn't define what's the ideal shape means. Yeah.
Yeah, I don't know. So the general message we usually our projects is how to say seeking is interaction or the iterative process is very important. So user usually don't have a specific goal or ideal shape in their mind. They only emerges with hands-on activity. So user do something and gets a result. And after looking at a specific instance result, then the user can refine the idea and then go back to the update the result. So I think this kind of interaction is important or critical for design process. However, it's often not focused in computational design system. So that's what we would like to say in our project results.
So actually, I have a question, also related to the subspace search. So I see in some example, so you have some actually you have some picture for the 3D or for the 2D image. So previously people can, with this input, people can optimize the latent code directly. Yeah, to because you can define some object function to let the result be similar to your input. And can you compare these two kind of approach using the subspace search and also using the automatically optimization?
So I don't know. So if you have the ground truth target data, you can use automatic method, right?
Mm-hmm.
However, our target is situations where you don't have the target data as something understandable by the computer, only in user's head. Then we cannot use any automatic methods. User have to judge.
Yeah.
So that's the idea. I hope you get the
I,
idea.
I got your idea. I mean, just because once you have some expectation. So you have some input, yeah, for optimize. So you have your subspace search method, and you have another using the just using the gradient descent method for optimization. So do you think it's possible that people can find a better local minimum for for the input? I mean, using the subspace search. So because you have a lot of supervision, yeah, during the optimization.
Oh yeah, so this differential subspace project sys method is essentially gradient descent. So it's essentially just trying to go to local minimum. So that's the overall framework here. So if you want to do global optimization,
Not global. I mean, you have different paths, but you always reach a local minimum, but maybe it's a better local minimum because each step you define a direction, yeah, to do
yeah,
the search, yeah. But for general approach, you just do the compute global uh, gradient and do the line search, something like that, yeah.
yeah. So again, if the system can get information, it can run some better automatic optimization. But if the user has to interact, yeah. But by the way, but if the user is not really like the current local minimum, you can just go completely different place using slider. No, I want to go more different area, then just move the slider completely different location, then just try to search local minimum around the new location. So user can stay away from local minimum if she wants.
Thank you. Yeah.
Oh, by the way, so in this project, this implementation, we intentionally didn't use direct sketching or direct modeling kind of interface, but that kind of content-based instruction should be combined for real applications, I think.
Okay. So actually, for the human in the loop, this concept, I think you also have some work for the reinforced learning. Using this, if I'm correct. So
Well, a couple of reinforcement learning for character bots like Mario play style. Yeah, so we just started. Yeah, reinforcement learning is something we are now trying to work on something. Yeah, it's ongoing.
okay, okay, yeah.
Sorry to interrupt, but I think the reinforcement learning might have a much potential in this direction because your reinforcement learning can learn some used intention or interaction, as Takeo talked in his talk, right? So this is really a nice, inspiring direction. So this is my comment.
Yeah, so my understanding is that reinforcement learning usually just agent move in the environment and get reward and do something get reward. But human in the loop, you can control the environment or control the reward. Then you can guide the learning process. Yeah, that's something we want to do.
Yeah, exactly. Actually, you can introduce human in the loop as well. Yeah, because the human can define the award function or the cost or something like that.
Yeah, exactly.
Yeah,
Yes.
yes. And the algorithm or the machine can interact with human for better results.
Yeah, I guess the difficulty we have is to find a good target problem relevant to graphics. Just automatic game bot or robot doing something is not so interesting for me, at least. I want to find interesting application of reinforcement.
Yes.
Using the
I,
real
I,
robot.
I have
Yeah. Yeah. Please go ahead. Yeah.
Okay,
okay.
so may I ask some high level topic or questions so that each of us can discuss about that. Yeah, actually, 3D design or modeling is still a very hard task. Yeah, so all of you are aware of that. So, yeah, and Takeo gave a very nice talk from different views. For example, with different constraints, we can define different tasks. We have physical constraints, so we have to use simulation in graphics, right? And then we have fabrication constraints. Or maybe we can have some high-level constraints, for example, the affordance or functionality of the objects. Because in real world, some objects have some high-level, for example, the saliency stuff, or the functionality, the dynamic actions, or some abilities of this object. So maybe we can introduce some affordance or functionality constraints in the design process. So do any of you have some ideas about that? Maybe we can figure out some very nice or interesting topics around this direction.
So you mean physical object, right?
Yeah, physical objects, or maybe in VR, we have to design a desktop, or we have to design a machine. The machine can move dynamically, but how
I
to
think
design this
my
kind of
understanding is that functionality is relatively easier to do in computer, right? Just be able to do something. But I still do not understand affordance can be difficult because it's very human.
the affordance means that if you have to grasp an object, how do your fingers to touch, or how do you determine the contact points of the object between the object and the fingers tips? So you have to understand the shape of the object. And for users, if he has to design a bottle or something like that, he has to understand the functionality of the bottle, or maybe he can express his intention in better way. So in my opinion, that we may introduce maybe other user or other constraints, something like the functionality or potence constraints in the human in the loop design process. That
Yeah,
might be
one possibility is integrate kind of virtual human kind of thing in a design evaluation.
yeah,
right?
yes, yeah.
Like hand shape or body size. Yeah, that's some possible direction. Yes.
Okay, yeah.
I'm thinking the function, including functionality in the computational design will be a trend, because when we design the object, we don't just want to fabrication. We also want to make use of the fabricated objects. So in this case, I'm thinking that, for example, we want to design a robot or a machine. Simulation is just one part of the analysis, and simulation just means it will work. But will this work satisfy users' intention? Then we might need to do some functionality analysis. It's more high level, but I agree that it's going to be a very interesting topic to be studied by graphics community.
Yeah, that's interesting direction. Human side thing. How human use it, how human interact with object is difficult purely numerical analysis. It needs machine learning kind of technique, right? So that's a very good opportunity to do. Yes.
But the other maybe more easier stuff is that to design the dynamic objects like robots. So the robots consists of a number of small parts, and the parts are interlocked or interconnected in some way, and they have to move in some specified movement, something like that. Yeah, maybe the design of such dynamic objects is more challenging. And I think there we will define or find some many interesting topics around this direction.
Yeah,
Okay, I have a view.
yeah, please.
Okay, I have a view about this. Yeah, so to my opinion, so it's more challenging to design these dynamic objects, especially assemblies, because it's involving to simulate their kinematics and especially dynamics. So it's more challenging. So in my opinion, actually there are two kinds of dynamic objects. One is conventional machines. They're purely based on this gears linkages, this mechanical parts to transfer the motion. And the other kind of dynamic objects is modern ones. It's robotics. is based on this motor and controllers to control the motion. So in the first one actually is more about the geometry design problem. So because it's the main task is to design the geometry of these mechanical parts, and then just simulate how they work together to transfer motion and forces. But for the second one is actually it's more challenging, and it's relevant to the control science. You don't just design the geometry, how to optimize the layout of the controllers and the motors. You also need to design the control algorithm. That's I know some researchers are doing research in this area. I think it's also it's quite cross-discipline and also quite challenging, but it's very promising. I mean, that's my opinion.
Yeah, at SIGGRAPH, I do see some design system for robots or drones, I think, with combining physical simulation and so on. And yeah, and I think we can do something by integrating more human in the loop aspect in that. Yeah.
Okay. So any further topics we would like to?
Okay, maybe I have another topic to want to discuss with all of you is that the style of computing, and Takeo talked about crowd computing or distributed computation of chip design. So do you have any idea around this? Because nowadays we have cloud computing architecture, we have lots of machines all around us, and how can we split the high computation into some distributed computation stuff or task for our human in the loop design tasks or something like that?
So you make cloud computing, so it's
Yes, cloud computing. So for example,
Amazon
in
AWS.
physical simulation, maybe some simulation is very slow, and then you cannot get interactive feedback for the design. So yeah, and maybe you can use some cloud computing resources to help you to return the fast simulation results.
Yeah,
Maybe
so we usually prefer local machine because we want interactive feedback. User do something continuously,
yeah.
system flows continuously. So network scale computation is a little bit too slow for direct manipulation kind of interaction. But if you can wait, of course, cloud computing resource may be more relevant. So yeah.
No, what I mean is that simulation might be very slow, and using local machine, you cannot get feedback in instant feedback. So how do you handle with that?
Well, typical approach these days is, offline computation, do lots of computation, pre-computation and training. And in runtime, you just, use the result from long pre-computation or training result. So that's a typical approach, I think, these days.
Okay.
Yeah, I also see a couple of works. Yeah, they just do some pre-computation. They have working on the special domain. So, for instance, the object you know the object the basic size, and they can do some simulation, the offline, and you can train something. Yeah, then in the runtime you can just predict. It's not very accurate, but it's good for your interactivity control. You can see the feedback and visualize the error, something like that, and then you determine the parameters and then send to the real offline computation to validate the result.
Yeah, exactly. For human in the loop, quick response is critical. And pre-computation and training beforehand is very effective approach.
Okay, I see. Yeah, just so machine learning can be helpful for this task. Yeah.
Yeah, acceleration. Yes, definitely.
Okay, I think we have a good discussion, and also the time is also is good for now. Yeah, to end our talk. Yeah. So thanks, Professor Igarashi again, and also thanks Li Gang and Peng. So let's see another time. Okay.
Yeah, thank you so much.
Yeah. Okay. Thank you.
Okay.
Bye bye.
Okay,
Bye.
thank you. Bye bye. Yeah.
You.